Well, Dr. Park Williams is a bioclimatologist and associate professor at UCLA's Department of Geography, and he's kind enough to join me on the Climate Pod. Dr. Williams, welcome to the Climate Pod.
Thank you very much. It's really nice to be here.
Well, it's so great to have you on. I'm just so in awe of climate scientists. I love talking to climate scientists. It's one of the reasons we do this show. And I'm always curious, what got people into this work? And you're in particular, you do a lot of great work looking at drought. So I'm curious, how did you get started in all of this?
That's a really great question. Probably just like anybody who finds themselves doing something as an adult, you can think back on it and remember a few events, and you wonder if that's the reason. But it's really tough to know, because also we end up doing the thing that we were interested in maybe in our early to mid 20s, and that ends up oftentimes taking. But there were some moments when I remember when I was in 5th grade, we would drive to elementary school every day, my mom and brother and I grew up in Northern California near the Folsom Lake, which is one of the lakes. If you see the media about droughts in California, oftentimes Folsom Lake is one of the poster childs of drought in California. And in the early 1990s, when I was in 5th grade and crossing the Folsom Dam every day to go to school, I watched the lake drain during a pretty severe drought that really gets talked about these days, 1990 and 1991. And I remember one day we were driving across the dam, and a radio story was playing about tree rings. And it was telling us about how rare an event like that was, because tree rings can tell us about the way that climate was behaving before we were around to observe it. And I remember being fascinated by that. There are more examples. I won't run through them, but there are events in my childhood that at least made me aware that I was really, really interested in this stuff. Whether or not those events actually caused me to be a climate scientist, I have no idea.
Well, tree rings it's so cool, because that is, even today, a critical part of some of the things that you research, right?
Yes, I think tree rings are awesome. When I was in college, I was trying to figure out whether I wanted to be an earth science major or a history major. And it was essentially a coin flip. And the coin ended up sending me in the earth science direction. But I always wondered if I had made the right call. And when I began using tree rings in my research, I felt like all of the interests were married. It is fascinating to me that we can look at the trunk of a tree, count back the rings, and see the year of the revolution, or even on some trees, the year 1 AD, or the years of the Roman Empire. It blows me away that while we tend to think about the quality of our lives on a day-to-day or maybe year-to-year time scale, if we could ask a tree how it's doing, it would probably say something more on the decade to century time scale. Oh, I'm having an okay decade, or it's been a tough century.
And so, you're recently just involved in this study that was looking at what's happening in Southwestern North America, especially in the last 2 decades, when it comes to drought. What were some of the main takeaways from the results of that research?
Well, we know that the southwestern part of North America, and when we say Southwest North America, I'm not talking about just Southwest US, but something much more broad. Really thinking about from southern Washington all the way down through northern Mexico, and from the Rocky Mountains west to the Pacific Ocean. And we know that the last couple of decades have been really dry. We've seen a huge explosion in wildfire activity, I'm sure we'll talk about in a little bit. We've seen giant bark beetle outbreaks killing off forests. We've seen rapid decreases in our largest reservoirs, lakes Mead and Powell. So we know there's been a drought, and it's lasted about 20 years, but it's tough to, when we have weather station records that only go back for a century at best, it's really tough to put that in context. But tree ring records tell us that if you look further back in time, you can find droughts that were truly massive. And the last of those droughts was in the late 1500s, from the 1570s through 90s. And that drought and a few others before it have been called megadroughts. And the reason they're called megadroughts is because when they were really being talked about a lot or discovered in the 1900s, they were by far and away the worst droughts or worse than anything that humans had seen during the 18 and 1900s, when climate events were actually being recorded. Of course, Native Americans survived these droughts, but not unscathed. There's a lot of evidence showing that the ancestral Puebloan society that created the cliff dwelling establishments in places like Mesa Verde, Colorado, and Chaco Canyon, New Mexico, had to depopulate those places during a mega drought in the 1200s. And so a question was, well, it's sure been dry over the last couple of decades. How does the drought conditions of the last couple of decades stack up against these so-called mega droughts? And what we found in the study was that if you look at the years from 2000, when the drought really began, through the year 2018, when we began doing the study, then those 19 years were actually as dry as the worst 19-year periods of the worst mega droughts that I was just talking about. A key difference, those mega droughts lasted a whole lot longer, or at least some of them. Some of the droughts lasted 30 years or more. And so we're not there yet in terms of duration, but in terms of intensity, it turns out that the last 20 years appear to be just as dry as the worst mega droughts.
And of course, the question then becomes, how much is this attributable to climate change, right? Because we know the last 20 years, the Earth has warmed. It's going to continue to warm. So when you're looking at that question, how much can we attribute to climate change? What did you find?
Well, we found that up to half of the intensity of this 19-year drought from 2000 through 2019 is due to human-caused climate change. I'll talk about why in a second. The reason that question was really interesting or important is because the mega droughts of the past of course occurred without human-caused climate change. And so that tells us that Western North America has the gigantic capacity for huge swings in what we call hydroclimate, or the climate of precipitation and evaporation on year to year and even decade to decade timescales without the assistance of human-caused climate change. So is this drought purely bad luck, or is it bad luck mixed with something that humans should take credit for? And it turns out that it is bad luck mixed with something that humans should take credit for, meaning this drought isn't entirely due to climate change, but about half of it is. And the reason is because of warmer temperatures. Today, the Western United States is something like 2 degrees Fahrenheit warmer than it would be without human-caused climate change, 2 or maybe even 3. And warmer temperatures promote faster evaporation as long as there's moisture to evaporate. And so the forests or the mountains of the Western United States have been getting gradually drier because of warmer temperatures. And it has been a bad luck drought, but the bad luck drought, if human-caused climate change hadn't been coinciding with it, the bad luck drought would have caused this drought to be something like a once per century or two event. Instead, this is an event that's as bad as anything that's happened in the last millennium.
Even if we mitigate on a very aggressive timescale, like as we said, warming is still going to continue for a while. Do we think our bad luck's going to continue with this drought?
Oh, well, we always have the hope that good luck returns, and the mega droughts prove to us that luck is a really big deal in the Western U.S. and Northern Mexico. So there is a chance that we could have a couple wet decades, even though temperatures are high. And I hope that we're lucky enough to have that. But as you just implied, global warming is really still in its infancy. And in the next few decades, we're likely to see the background temperatures of the Earth warm substantially more. In the next 30, 40 years, they could easily double the amount of warming that we've had in the previous 30 or 40 years. And so good luck will come, bad luck will return. And each time the bad luck returns, then very likely the drought will be worse than it would have been if global warming was not occurring.
Let me ask a real dumb question, which is something I often do on this podcast. When I think about drought, I'm thinking about rainfall and temperature, right? How much precipitation is there that's getting to the ground, and then how hot is the temperature to evaporate that precipitation? Are there other factors that go into drought?
Precipitation is the source of all of our moisture, but evaporation is always occurring as well, taking water away from water that we could possibly be using. And there, you mentioned temperature, and that is one of the key variables, but there are others. Solar radiation is one. So is it cloudy or clear? And are you close to the equator? Are you close to the poles? You're getting a lot of sunlight or a little bit. That's important. The more sunlight you have, then of course, the faster things are going to evaporate. Humidity is also really important. So temperature, a warmer day on average is going to evaporate water. Say, think about a puddle on the sidewalk, for example. A warmer day is going to evaporate that puddle quicker than a cooler day, but the pace at which the warm day can evaporate the water is going to be modulated by humidity. So a puddle on a New York City summer day isn't going to evaporate as quickly as a puddle on a Los Angeles summer day, because New York City is more humid than Los Angeles.
So, not only are you digging deep into the climate science, but I know you also think about the societal impacts of what drought means. When we look at some of the human impacts that we can see in higher occurrences of extreme drought, just thinking about it in the West, what could happen in future years as a result of extended drought?
Oh, geez, if water disappears from a location, then people can't live there anymore. And it's as simple as that. We've seen examples during these droughts in the West, during the worst parts, when water actually becomes totally inaccessible locally, and small towns have had to be shipped water, shipped bottled water. Toilets have been moved to the street, so people going to outhouses, people washing dishes with bottled water. This has already occurred on small scales or in small communities that have run out of water because their wells don't hit the water table anymore. Our large cities, and I tend to think about the Western United States because that's where a lot of my work is, but globally, large cities cannot exist unless water is being brought into those cities at very rapid rates. Los Angeles and other large cities in the Southwest are really dependent on water being shipped from very far away. And if that were to fail, then we could see whole cities in very quick peril. Those aren't the only examples. Across the United States, including where you are in Indianapolis, we've seen people exposed to smoke from wildfires this year and last year, and increasingly over the last 40 years. Now, fire is, of course, a natural phenomenon that has occurred without people. Fire has been on Earth's continents for the last 350 million years, and is critical for ecosystems. I want to say this to make sure that none of us think that fire is just inherently bad, but we have seen a rapid increase in the rate of very large, severe fires in the Western United States, and we may talk about this a bit later, but those coincide with heat. And as the Western United States, Western Canada, Northern Mexico, and other areas with more Mediterranean-like climates have warmed, we've seen big increases in the size and intensity of fires. And it's not just the people living in those areas that are burning that are being affected, but remote places like New York City, for example, was exposed to Western US smoke pretty heavily this year.
Yeah, and I think it's kind of obvious. Well, drought creates drier conditions, obviously, and that creates fuel, which is easier to burn. And we obviously see this in the California wildfires. But let's drill down. Like when we talk about fuel for fires, what does that mean?
Well, when we talk about fuel for fires, we're mainly talking about vegetation. Think about what you would put in your fireplace if you wanted to have a fire. And this is actually where we're presented with a little bit of a paradox, because the only way that you can have fuel is by having moisture. Of course, if you don't have moisture, you have a desert, and we very rarely see wildfires burning through the driest deserts on Earth. We instead see wildfires, the most intense wildfires, burning through relatively wet places. But as long as you have enough moisture to grow fuel, then suddenly what we call the fire regime, or really just the way that fire burns, the fire becomes dependent not on fuel, but on dryness. And so over the last 40 years in the forests of the Western United States and Southern Canada, there's plenty to burn. All we need to do is dry it out. And over the last 40 years, we have seen warmer temperatures, reductions in summer precipitation, and as a result, drier fuels. And then, even though ignitions are pretty chaotic, they either come from lightning, which actually coincide with storms, or from people on a pretty random basis. And then, even though we try and put out the fires, still just as hard as ever, fires are escaping our control increasingly frequently. And it's because of the drying out of the abundant fuels.
So I think it gets into this. I mean, obviously, since you are a California native and a California scientist, we always think about why are fires so bad in California. If I understand you correctly, so we kind of have this balance where there's enough moisture for things to grow, but then those things can dry out and then they become accelerants to burn. Also, obviously, we have warming temperatures, but there's also a lot of people in California. What role does that play in exacerbating these wildfires?
That's a great question. It's actually harder than you would think to figure out, because people have a number of really important impacts on fire. Of course, so in California, something like half to 3/4 of the large fires are ignited by people. That means that we shouldn't discount lightning. Lightning is a really important source of fire as well. They're not all caused by people. But something like half to 3/4 of large fires are lit by people. But people are also very good at putting out fire. And so if we just compare a map of fire occurrences, fire locations, to where people are living, we actually see that it's harder to get big fires near populations than it is far away from populations. There are a couple of reasons for that. But a primary one is that even though people are sources of fire, they are also sources of fire suppression. And they're better at putting out fires than they are at lighting fires, perhaps. Whereas if you're out in the middle of nowhere and you get a lightning either from a person or from if you get an ignition from a person or from lightning, then you are likely to see that fire turn into a really large fire as long as the moisture conditions are right. So that's a long way of saying that California's got a lot of people, but if you, I guess this is a great way of answering the question far quicker. Even though California has a lot of people, and even though the population of California has grown a lot in the last 40 years, the number of fires per year, or at least number of large fires per year, has not increased very much in California. Instead, it's the size of the fires that's increased. Right. And so what that tells me is that it's not the population that's driving this, but it's something about the way that fire spreads. Fires are escaping our control more easily today than they were 40 years ago, even though there are more people and more resources available today to try and put out the fires. But conditions are drier now, and so fires are able to move through dry fuel much more easily today than they were when they were trying to move through wetter fuel 40 years ago.
Studying this and talking to other climate scientists that is there a worry that fire suppression efforts are contributing at all to increased wildfire size?
I think so. Logically, it does make sense, and this is a bit of a paradox that fire suppression would actually lead to larger fires, and the reason is, or the way to understand that is think about the long term. In the late 1800s or mid 1800s, even, we weren't so good at suppressing fires. But fires started disappearing initially because European Americans introduced grazing on really large scales. We had sheep and cattle grazing grass across the Western United States, reducing the continuity of fuels. Grass is really important for carrying fuels, and when grass started disappearing with grazing, then fires started getting smaller. Then the early to mid 1900s, we started putting a really high priority on suppressing fires. The Forest Service started becoming the Forest Fire Service. And they developed a policy that whenever a fire was spotted, it should be put out by 10 a.m. the next morning in the first half of the 1900s. Every time we successfully put out a fire, then if we don't do something to thin out the vegetation the way that the fire would have, then of course the vegetation is allowed to continue growing. And so just like if you loaded your fireplace full of wood and then decided to not have the fire, you wouldn't need to load the fireplace with new wood the next time, you just burn the old stuff. And the difference here is that the forests, of course, continue growing. And so not only were we kicking the can down the road every time we suppressed a fire, but we allowed fuels to continue accumulating. So when the eventual fire did happen, there'd be more fuels available than there were previously. And that means that many of today's fires are burning through vegetation that's more dense and therefore more fuel available than would have been the case if we had not been suppressing fires for the last century. So there's just no way that our fire problem today isn't linked to our fire suppression problem. The question then is, or the question I'm often asked then is, well, which is it? You just said that a warming and drying climate is causing the increase in fire. And now you're saying there's no way that fire suppression isn't partly responsible. And all I have to say is, I'm sorry, it's just not that simple of a world. You can actually have multiple things going on at once. An extreme example is this. If instead of allowing fires, if instead of allowing forests to continue accumulating biomass over the last century, let's pretend we eliminated all forests and we turned the entire Western US into sand dunes, then no matter how much global warming we had, we'd have no more fire. But instead, we've done something that really set the table for global warming to be able to have a big impact. We allowed many forests in the Western United States to become overly abundant in fuels. We allowed the forest to accumulate what scientists refer to as a fire deficit. And we are now paying off that deficit. And we would have, even without climate change, but the pace at which we're being forced to pay off this deficit is being impacted majorly by climate change. And the reason I know that is because when we compare the sizes of fires to the climate, or the area that is burned annually to the climate, specifically the dryness of the atmosphere, which is set by temperature, then the correlation is actually shockingly high, where the climate explains not only the year-to-year swings in how much area burns, but it also explains the trend that we've seen in the last 40 years. In the last 40 years in Western United States forested area, the annual area burned has increased by over 1,100%. That means that more than 10 times more forest is burning in an average year today than in the 1970s and 1980s. And that increase coincides exactly with what you'd expect based on the increase in temperature.
That's astonishing.
The overabundance of fuels set the table for that to happen.
Well, I think like you're talking to people listening to this show, you don't have to convince them of mitigation, right? We have to stop burning fossil fuels. I think everyone knows that who listens to the show, but then it brings in the adaptation questions. When you see this, what the hell do we do about it?
Right. So this is a local problem caused by a global problem. And the global problem on your podcast, you guys talk a lot about, and it's really, really important to figure out what we're going to do about our global carbon problem. But the global carbon problem is causing a diversity of issues at local scales. And locally in the Western United States and Southern Canada, one of the problems that we're seeing is a huge increase in the rate at which forests are burning near people. And so what are we going to do about that, accepting that no matter what we want, the globe is going to continue warming for the next few decades, maybe fast, maybe slow, but locally fire is going to continue getting in the way of our lives. And so there are a few things that can be done. One, I think we should think more carefully about where we live. I would love to live in the forest. When I was a kid in the 80s and 90s, I dreamed of living in the forest. But today I know that the fire danger conditions in the forest are really high. And so this is going to be, or should be, reflected by living choices in the next few decades. the population of people living in harm's way has been going up at the same time that fire has become more and more problematic for communities living in forests. Part of the reason is because we keep putting fires out in these places, and we're kind of stuck. As long as people live in the forests, then it is kind of a moral obligation to stop these communities from burning. But every time we do it successfully, it may give the false impression that these are safe places to live. But also, assuming we do want to continue fighting fires in areas that we really don't want to burn, then we need to take responsibility for doing the work that fire would have done for us as far as thinning the fuels. And that's a really hard job. There are two ways that it can be done. The first is by lighting fires ourselves, doing controlled burning. And the second is by thinning vegetation. That means going out and cutting down vegetation and thinning the stocks of fuels that are in our forests and other plantable ecosystems. Both of those are very expensive, and neither of those is a one-time fix. If we're going to start doing, or we do this on small scales, but it needs to be done much larger if we want to have a difference. If we want to make a difference and actually do the work that fire would have done for us, wildfire would have done for us, then it's not a one-time thing. It's something that we need to do like every 10 years. Now, for people in the East, especially, it's tough to imagine just like how vast the forests are of the Western United States. There is far too much forest to do prescribed burning through or to be thinning once every 10 years. And so instead, we need to prioritize. We need to figure out where are the places that we really, really don't want to burn, and is it feasible in those places to thin the fuel stocks enough to actually reduce the danger of fire. And that is going to be even that local thinning and local fire suppression is going to be a gigantic investment, a huge commitment of money. Right now, the vast majority of money that we put into this whole fire problem is on the back end, or I should say, it's on the crisis management side. The U.S. government will basically write us a blank check every year to fight fires as hard as we can. They love seeing the helicopters in the sky. They love seeing us going to war against the fires. And that money then takes directly away from the money that we have to do preventative maintenance.
Yeah, and it's just so crazy because, and if we're not mitigating the problem, it just increases the scale of it, right?
That's right. And a great example is this year. So this year is a really bad fire year. Last year in the West was a bad fire year. This one has a chance at matching last year, especially in the states along the West Coast. And as a result of the really high fire activity this year, the chief of the Forest Service announced last month that we are going to stop this year doing all other activities on the proactive side because we're spread too thin on the reactive side, meaning no more prescribed burns the rest of this year and no more use of wildfires. What use of wildfires means is sometimes when a fire gets going, if it's burning in a place that experts know needs to burn, and the chance is really low of that fire turning into a fire that burns through a human community, then sometimes we'll allow the fire to do that, which in my view is a very healthy thing. The Forest Service has announced that we'll no longer be doing that in 2021 because they're spread too thin fighting the fires. That results in a major lost opportunity because the whole United States the fire in forests over the whole United States. This is a really large area. The problem right now is in the western West Coast states. There was just a great monsoon in Arizona, New Mexico, and southern Utah and southern Colorado, where there are a lot of forests that are overstocked with fuels, and that reduces the fire danger in those areas right now, giving a very unique opportunity to be able to have prescribed controlled burns under conditions where the fires are much less likely to escape our control. But our Forest Service reacted politically rather than scientifically And as a result, we're losing that opportunity, continuing to kick the can down the road, doing the same thing that we've been doing for decades.
That is nuts. And I didn't know any of that. I'm curious, as you mentioned, 2021 has been another bad fire year. And I was, just monitoring this in the months leading up. I could tell that, well, it was a drier year, right? Like, has there been anything that has surprised you looking at the drought in 2021 and the fires, looking at that landscape? Has there been anything that surprised you by what's happened?
Oh, there's probably not a single climate scientist who wasn't surprised by the intensity of the heat wave that hit the Northwest in July of 2021. That heat wave was absolutely insane. Portland, Oregon, hitting something like 114 degrees. I don't think that Los Angeles has ever hit 114 degrees, although last year they hit 111 degrees. And that shocked me as well. The intensity of heat waves recently has been shocking to me. And so if you look at when the fires get going in the Western United States and when they have their biggest days of spread, it's during the really hot, especially like summer fires in particular, it's during intense heat waves. And the thing that shocks a lot of people, but doesn't shock those of us who've been looking at the data for a while, is the spread rates of these fires during the heat waves. It is now common to have fires spreading at rates of more than a football field per second for 24 hours in a row. So if you ever hear about a football field is roughly an acre. And if you ever hear about a fire that spreads more than 85,000 acres in a day, that means more than a football field per second was being burned. That is shocking. That was shocking to me until I realized that the rate of spread of fires increases exponentially. And it's similar to the way that the size of the area of a circle increases exponentially as you increase its radius linearly. And the reason why this is important with climate change is that it means that for every degree of warming that we have in the West, or really anywhere on the planet, the potential for fires to grow increases much more than it did in response to the previous degree of warming. And so when you hear people on the radio or on TV saying, I've fought fires for my entire career and I've never seen fire activity like we're seeing this year, it is because fire is responding to climate change in a non-linear way. And among all the things that we care about in climate science, it's the non-linear ones that keep us up at night, because the Earth has proven, and it stores records of this through a bunch of different ways in the paleo evidence for us. It's proven that it does respond in nonlinear ways, and given a hard enough kick, it can move into a totally new setting. What we're seeing in the West when it comes to fire is a incredibly rapid ramp up in wildfire activity that could very well leave many Western mountains that have been forested for many millennia unforested, turned into grass and shrubland. Now that on its own may not be such a bad thing for everybody, but it certainly is a huge dramatic transition that we should be thinking about and understand.
And we have this UN report that comes out just a couple of days ago that says we're currently on pace for 2.7 degrees Celsius above pre-industrial levels, right? So this is more than a doubling, almost a tripling of the warming we've already seen. And as you mentioned, that doesn't mean a doubling or almost a tripling of the impact. It's going to be non-linear. It's going to be exponential. When you think about that from the lens of drought and wildfire, what could that mean about the future we're heading toward?
Oof. In the last century, the globe was warmed by something like a degree Celsius or 2 degrees Fahrenheit. On continents, it's more like 2 to 3. Thinking about another 2 on top of the 1, this is the global mean. Thinking about another 2 degrees on the global mean, in addition to the one that already occurred, meaning that on continents, something more like 4 degrees Celsius on top of the 1/2 to 2, the changes that we would see are astronomical. And it sounds like I'm just imagining here. But the Earth, if you look at, like, I guess wildfire is a bit of a canary in the coal mine because it responds exponentially. We get to see it early. It's proving to us. If you look at the year-to-year swings in temperature, they match almost perfectly with the year-to-year swings in area burned. It is wildfires proving to us the nonlinear responses of the Earth system to warming. And there will be some places where they could actually benefit from warming. There will be some places, many places, that are worse off because of warming. The rate at which these changes are going to occur, though, will be profound if these places are sensitive to temperature in nonlinear ways, the way that wildfires have been in Western North America.
You obviously can't live in places that burn down, but as we were talking about earlier, with regards to drought, that really puts a lot of places in jeopardy as well. And as you were saying, you can ship people water, but that becomes, possibly increase in cost, and it's obviously a political decision, right, to ship people water. I'm curious, when it comes to drought, are there other ways that you've seen communities adapt to having like less water? Like, what can people do to adapt to drought?
People do adapt to drought. If you look at Las Vegas, for example, the per capita water usage in Las Vegas over the last 30 years has plummeted. It's still higher than national average because it costs a lot of water to live in Las Vegas. But Las Vegas and other cities in the Western United States have actually proven that people are quite adaptable when it comes to water. Traveling around my current home city of Los Angeles, I see a lot of water being used on things to make things look nice, or at least the way that we learned to look nice in the 1900s, such as a lot of lawns, a lot of golf courses, and those aren't inherently a bad thing, but they will become increasingly unsustainable as the crunch on water occurs. But it's actually encouraging to see those nice things now, because I know those are things that will be relatively pain-free to let go brown. So there's a little bit of fat in the system that can still be trimmed. But I think that there are some places on the planet where decreases in water availability are already occurring and will continue to occur, and they're going to have massive impacts on what people can do where. In the Western United States, agriculture is the thing that is going to have to transform in the next 50 years. I'm not going to get into specifics on agriculture because I don't trust myself. I'm not an expert on agriculture, but if you look at the numbers, the Western United States, about 80% of water use by humans goes into agriculture. And so if we decide that we don't have enough water, and we have, then at least say south of the Oregon border, then we have to use less water. And the vast majority of the pie on where those water cuts can come from is on the agricultural side. Cities have shown that they can use less water, but that's going to be probably a drop in the bucket compared to what the water cuts that actually need to occur. I said earlier, this drought in the West is as bad as anything we've seen in the last millennium, but to many, it doesn't really feel like that. It feels like, well, we're doing okay here. One reason is because we have been relying on groundwater to get through this drought. The Central Valley of California, for example, has been drilling water out of the ground faster than ever before. And you can actually see evidence of this as the elevation of California's Central Valley has actually sunk by several feet over the last few decades, just like a sponge getting squeezed out. This water is getting harder to get. In some places, it'll become impossible. In other places, it'll still be possible to get groundwater, but you need to drill further and further. So we should think about who is able to drill further and further. Certainly not the single-family farmer who has been trying to make ends meet through this drought for the last 20 years. As groundwater gets harder and harder to get, then we will very likely feel the water limitation problem that has been accumulating in the West harder and harder in the next few decades, unless some giant new technology comes online at a really rapid scale, like a discovery of how to drill really deep for water, or desalinization of ocean water on really, really large scales.
About how much of the United States do you think in the West is experiencing drought?
Well, as of May and June, actually, up until early July, it was, I think, over 90%, according to the U.S. Drought Monitor. The U.S. Drought Monitor has been trying to keep track of this in a quantitative way for the last 20 years or so. And
wait, 90% of the entire United States?
No, I'm sorry.
Oh,
I'm sorry. I'm sorry. Yeah, do you want me to start over?
No, you don't have to. I was making sure that I was like, oh my gosh, that's a lot.
No, yeah, you're right. 90% of the Western United States, as of early July, is something like 90%. I don't have the data in front of me right now. Something like 90% of the Western United States was experiencing drought of some magnitude, meaning drier than average conditions. Now, drier than average conditions we can deal with, but what was really record-breaking about 2021 was the proportion of the Western United States that was experiencing what the U.S. Drought Monitor refers to as severe or extreme droughts. These are the highest classes of drought, and it was something like 2/3 or 70% of the Western United States, by my calculation, from August 3rd through August 17th was classified as extreme or severe drought. Meanwhile, the Eastern United States, of course, has been wetter than normal in 2021. The Northeast was really wet at the end of an exceptionally wet June, and then they were hit by a tropical storm, and then they were hit by another tropical storm. The Eastern United States, in fact, over the last 20 years, has been wetter than normal, and over the last at least 120 years has been getting wetter. Whether or not this is due to human-caused climate change or natural variability is still up for debate, but it is pretty striking. If you look at the average of the United States, then looks like the United States is not really experiencing drought due to climate change. But if you look at the East versus West, you see that the Western United States has been drying and the Eastern United States has been wetting.
What was happening in the Colorado River? That was such a big story. What was going on?
In 2021?
Yeah.
Well, it was dry. Like the 2021 was super dry. By my calculations, soils across the Western United States were as dry in 2021 as they were in 2002. Before 2021, 2002 was really the signature year of the 2000s drought. Of the 22 years since 2000, I think 18 have been drier than average in the Western United States, but 2002 blew all of them away. In fact, 2002 was the driest year since at least 1729 in the West. 2021 matched 2002. So it was a really bad year. And this is a year we're going to be hearing about for the next several years as the consequences of 2021 play out. For example, very likely new large bark beetle outbreaks will occur across the Western US as they did in the years following 2002. But the reason why 2021 got so much news on the Colorado River was not only because of the conditions specifically in 2021, but because in 2021, the levels of both Lakes Mead and Lake Powell, these are the two largest reservoirs in the United States, both hit record lows. Now, those years are gigantic, those lakes are gigantic. So they don't fluctuate much on a year-to-year timescale like the Folsom Lake that I grew up near in Northern California. Those lakes instead fluctuate more on scales of 5 to 10 years. And so when you hit a record low in those lakes, that means something's been going on for a while. And so in 2021, we saw record lows because of a combination of near record-breaking drought conditions in 2021, combined with the fact that 2021 occurred right when everybody was hoping this 20-year drought would be ending. And instead, 2021 shows us that we're just as much in the thick of things as we have been at any other time during this 22-year drought period.
Let me ask you, to kind of changing gears here, let me ask you another climate science question, which is predicting temperatures or like modeling out temperatures. I know there's that that might differ than modeling out precipitation patterns. It seems to me like modeling precipitation patterns is a lot harder. So when you're trying to model that out as a climate scientist, like why is that more difficult than temperature?
Yeah, uh, I've been thinking a lot about that question too. And the first answer is simple. Greenhouse gases cause the globe's average temperature to warm. And as the globe's average temperature warms, then almost everywhere on the planet's temperature is going to warm. And so it's pretty easy to connect those dots. With precipitation, though, it's a lot harder because as you increase the temperature of the Earth, you actually change the way that the atmosphere circulates. And that changes the locations where precipitation occurs, and it changes the intensity of precipitation. And as it turns out, in a warmer world, there's actually more precipitation than there would be in a cooler world. So our last ice age ended about 15,000 years ago. During the last ice age, there was actually less global precipitation than there is today. However, it's also warmer today. And so some places today will get less precipitation because of changes in atmospheric circulation. The Southwestern United States and Mexico are one of these places. The Mediterranean is one of these places. Central to southern Chile is one of these places, and perhaps parts of Australia. And these same places that are projected to get drier and that have been getting drier over the last century, at the same time are still prone to larger than ever, higher than ever intensities of precipitation. So you can have both a decline in moisture availability and an increased risk of floods because of massive dumps of precipitation all in a single event. So the distribution of water across the continents and how it responds to climate changes is very interesting. And one of the most important things, perhaps more important to understand than just the amount of degrees of temperature warming we're going to have, is how is the distribution of water across the continents going to change. Just 5,000 to 9,000 years ago, when the locations of the continents were all the same back then, everything was the same 5,000 to 9,000 years ago, except that the northern hemisphere was getting more sunlight than it does today. As a result of that difference, not in the amount of sunlight for the globe, but where the sunlight was most intense, Northern Africa, the part of Africa that is currently the Sahara Desert, was lush with life just 5,000 to 9,000 years ago. There's paleo evidence all over Africa, Northern Africa, including evidence from people, cave paintings of wildlife. Today, there's still crocodile. Sorry, I always get these mixed up. Alligators and crocodiles still. Crocodiles are still stuck in oases in parts of the Sahara Desert that were basically just they're stranded there after this time when there was enough precipitation in North Africa to support abundant life. So that's the most recent example that I refer to in thinking about how changes in Earth's climate, whether due to humans or due to natural variations like the amount of sunlight the Northern Hemisphere receives, can lead to profound nonlinear changes in who and what can live where because of changes in where water is.
And the visibility of those changes, I think, is often one of the things that resonates the most with people when they think about climate change, regardless of whether they're in this every day or a week or not. And I think there was a story today where I think it was firefighters wrapping foil around sequoia trees. When you see things like that, because obviously you're talking about earlier, like when you're a kid in the 90s growing up in California, it's not like you hadn't seen changes in our environment before. But when you see these things, when you see people wrapping foil around trees and all of the weirdness that is coming with the way the world has changed just in our lifetimes, like, what are you thinking?
Oh, I have a 10 and a half month old son now, and so I see things differently than before because with some good fortune, he'll live to see the year 2100. With good fortune, I'll get to see 2070. And so he's going to see a lot of this play out. The nonlinear response to fire, in particular, to temperature, have me pretty confident that he's going to see a totally different Sierra Nevada mountain range than the one that I grew up in. When we're putting foil around trees to protect them, for one, these are really special trees. The trees that are being wrapped in foil. You can't wrap all the trees in the Sierra in foil, but in Giant Sequoia National Park and Kings Canyon, that's where General Sherman and the other largest trees on the planet live, and we don't want to see those burn. And last year proved to us that these giant trees, they're actually evolved to tolerate pretty hot fire, are now really susceptible to the types of fires that can burn through the southern Sierra. When I see that, though, I guess I wonder how long we're going to continue having to do that. These trees, General Sherman is probably over 2,000 years old, maybe 3,000 years old. Its existence proves that that the types of fires we're seeing today are rare, and the fact that we're tinfoiling it proves that we acknowledge that. This is a tree that has survived very likely hundreds of fires before, but now we think that it's in major danger. I'm not answering your question all that well, because it just kind of, it's depressing seeing those questions and seeing those pictures that led to your question. And I don't know. At the same time, I hope, like, they've been in our national parks, we've been managing our forests a bit differently, where prescribed burns have been occurring. We have been doing thinning. If you walk around this area where the truly giant trees are in Sequoia, there's not a whole bunch of ground fuel. These forests are not overgrown the way that other places are, because of good management in recent decades. And so I'm hopeful that this fire that burns through Sequoia is what we can think back on as a good fire, and not the type of fire that decimated a forest that has so far proven itself able to withstand fire for the last few thousand years.
Yeah, it's hard to put into words, but I can tell you one thing that I can put into words, which is we did not have phenomenal scientists like yourself and so many others to explain to people like me and people that listen to this show, and the people that care about this, exactly what is happening, exactly what is at risk. We would be so lost. So I'm just so thankful for your work and thankful so much for your time. Again, we'll link to the recent paper we were talking about. You're also on Twitter. You're at Pete W. That's at PeeDubLya. I'll link to that in our show notes as well as your website. But Dr. Park Williams, thank you so much again for joining the Climate Pod.
Oh, thanks a lot. I think this show is great, and it's an honor to be on it.